So, good morning, everybody. There's still some lazy guys that are still not here in the rooms, but we have to start since we are in Switzerland and we have to be precise and respect the schedule time. So, it's a very big pleasure for me to welcome you to the day 4 of the BImBS School, and particularly the first speakers. Outstanding scientist is here. We thank very much Modesto for coming. So, Modesto Orozco from Barcelona. He is going to speak about multiscale simulations of DNA. Thank you, Modesto. The stage is yours.
Thank you, and thanks for the invitation. So it's my duty today is to tell you about DNA, and considering that you have previous days some lectures on bioinformatics, I'm gonna tell you about simulation of DNA. So. Just to help me, I mean, can you raise hands based on your expertise? So how many of you are chemists? So I'm a chemist. How many of you are physicists? How many of you are mathematicians, computer scientists, bio something, biomedical, biotechnology? Absolutely scattered. Yeah, it's completely randomized. Okay, good. So I will tell you about DNA. DNA is, at some point, it's like proteins or atoms in the space, but from another point of view, it's completely different to proteins because it has a much larger size scale. When you think about DNA, you immediately came into your mind the work of Watson and Crick. It's probably the individual discovery of largest impact in the 20th century. So Watson and Crick were actually they were in a race trying to discover the structure of the duplex of the DNA. Actually, they realized that the DNA was a duplex, contrary to other people that think that was a triplex. And when they get the structure of the duplex, they realize that actually, yes, the structure explains how the genetic information was transferred. So it was a very clever structure. The DNA was like 2 strands, self-complementary, and because of that, it's very easy to realize how the information transfers from generation to generation. The duplex is open, and then one strand copy the other strand, and then you have exactly the same genetic information that the ancestors. How the duplex information transfer into proteins, it took a few more years, actually. There were very esoteric ideas from Watson, and it was actually Crick who deciphered what is called now the central dogma of biology. So DNA goes into RNA, and then it goes to proteins. And this intermediate molecule was a kind of messenger suggested by Crick that was actually discovered later that was true. But I want to, you know already all this, but I want to emphasize other aspects of DNA that is not only the biological aspect. So DNA, for the chemists in the audience, is a fascinating molecule from a chemical point of view. You can do incredible things with DNA. It can be probably the molecule in the future for biotechnology and obviously for biomedicine. And this comes for 2 intrinsic characteristics of DNA. One is the resilience, and the second is the ability to store information. And I like this to present in this way. This is believed to be the oldest document of human. Of course, things human did were paintings in the cave, but you cannot claim that these were really documents. This was the first document we have evidence. And it's a stone, it's a diorite stone, it's in Palermo. It's called Palermo stone. It's not a complete document because it was damaged, but it's really impressive. It was made in the 5th dynasty of Egypt. This is what is called the Old Empire. Just to focus your mind, the pyramids were in the 4th dynasty. So it is a little bit after the pyramids. And very impressive. It's more than 4,000 years, but it refers to information that came from what is called the archaic empire. So this is more than 5,000 years ago. And it's believed to be correct. So it is a kind of listing of the kings of the first dynasty, and we still believe that this list is correct. So very impressive, but you can see it's damaged. Remember, around 4,000 years old. And how long has the DNA stayed? Okay, this piece of stone lasts, with a meshes, lasts 4,000 years. How long DNA stay intact? So we have evidence of the first humans' genomes from Africa, and this genome has been sequenced without no errors. So it's like it was sequenced your genome. It's around 17,000 years old. This is the draft of the Neanderthal genome. It's not completely clear the age of this. Actually, it was a male from Neanderthal philia, but it may be between 100 and 200 years old, 200,000 years old. And it has some errors, mostly related to the methylation to the deamination of cytosine. So it was, at some point, it was not clear whether it was a thymidine or a cytosine, but just you have something like 99.something% of fidelity, and just using the human and the chimp genome, you can reconstitute. It's believed that without significant errors, the genome of something that was around 100,000 years ago. And this is, to my knowledge, the oldest mammal we have sequenced. Is actually a horse from the Pleistocene. And the errors are believed to be small. So this gives you an idea about the resilience of DNA. So humans have been able to make something that lasts for 4,000 years. Nature has made a molecule coding information that lasts for at least 700,000 years with a much lower error. And now think in all the technology you have around to keep information, and think if the information you have there is going to be valid in 10 years. Probably everything has been lost. Is this saying something for the future? I think that yes. And this is a nice work by a friend of mine, Ewan Burney from EBI in Cambridge, that actually was, to my knowledge, the first one to realize that actually we can use DNA to store information. And in my understanding, probably in the future, the big storage of information will be DNA-based. So what Ewan and co-workers did was to invent a code to transform information. Instead of bins of information, it translates into tetrads of information. So the 4 bases, it is called the Huffman, code. And then they took a different type of data. So Shakespeare sonnets, the Watson Crick paper, a photo, the speech of Mark, blah, blah. So they code actually into DNA sequence. They synthesize the DNA. They send by regular mail. Actually, they miss. They send the sample to the UK instead to the EMBO lab in Germany. So at the end of the day, the sample arrived to Germany. It was sequenced, and actually, the errors made by all this process were smaller than the errors made if the information was transferred through it. So we can really store incredible amount of information in DNA, and probably more if you use modified DNAs. And this is a recent paper appearing in Science this year, and is what is called the Hachimochi code. And this is what you can store information. Instead of 4 letters, that is that nature uses, you use 8 letters. So you play with modified nucleic acid. So it's really the DNA, and this is my last introductory thing, is a treasure. So you need to think in DNA not only as the molecule of life, something that is storing information in nature, but something you can play with, and actually you can make a very powerful molecule in terms of storing information, transfer information in a very resistant way, and actually as a tool in biomedical research, especially in what is called anti-gene-based therapy. As I told you in the beginning, so DNA has many things in common with proteins, but also have, and is the multi-scale nature. So when you work with DNA, sometimes you need to work a very, very small details. So, and then you can go to the quantum chemistry kingdom. In others, you need to tackle with the entire chromatin fiber. To give you just numbers, when you work here, you are interested in details that are below the Armstrong. So an error in 0.2, 0.3 Armstrongs in a hydrogen bond kills the interaction between a transcription factor and the DNA. And it can give to the death of the cell. If you go to this other level, you study the entire chromatin fiber. In humans, it is 2 meters. So you have a problem of 10 to the 11 in terms of the size of the system. And this means that if you play with DNA, you need to play with multi-scale modeling. So the physics that is valid here is completely useless here. It's valid, but it's useless. And on the contrary, the type of resolution you have when you deal with the system is completely useless if you want to understand something at this level of detail. And what my group and others have been doing for several years now is trying to develop a kind of continuum of methodologies, and this is what you are going to, I'll try to explain and what you are going to play with in the practical course. Okay, let's start. And let's start by the very first level, the quantum level. And I'm not going to give too many details because I prefer to give you examples. So I will make a very short introduction on the theory, and then I will expand a little bit more on the theory behind. When you work at this level of resolution, very small systems, but you need high accuracy, you have quantum mechanics. And in the DNA world, I would say that there are very few pure quantum mechanical studies, because DNA is determined by electrostatic interactions, which are easy to reproduce, but also dispersion, that is a pain in the neck. So there are very few full quantum mechanical studies on DNA. And most of the studies are done in the KMMM formalism. To my knowledge, the first people that formulate this idea of the quantum mechanical molecular mechanics type of calculation were Mike Levick and Aaron Warshall in the 76. And actually the basic idea is very simple. So you have a system that is very large, and there is a region where there is something where you need to focus a lot of attention. And you want to study this in very big detail, but you don't want to really lose the rest. So the idea of the KMMM approach is that you focus in this specific region, and here you will treat the system in high detail by means of quantum mechanics, with all the electrons, with everything. And then you have a boundary that is going to be classical and represented then through molecular mechanics potentials. The first implementation of the KMMM formalisms are used today, but are not the most used ones. It was called empirical valence bond theory. It was developed mostly by Aaron Warshall. So the idea was very simple. So you ran the simulations for one of the quantum states. Let's say that this is a reaction, this is reactant, this is products, and then you ran the simulations of the reactant, of the product, and you transform in a model system one to the other, and then you feed the quantum mechanical curve with a kind of classical potentials. Let's say like a kind of Morse potential, combination of two Morse potentials, and then you add a kind of resonant mixing terms that allow you to move from one to the other. Once you have this, you you can run everything at the classical level, but with a part of your classical potential that has been parameterized quantum for this specific reaction. This is what you can find in all the software from Ariel Warshall or Johan Aquist. And in the very basic formalism, you can find this in what is called reactive molecular dynamics. The most common implementation of the KMM formalism is what has been pushed by many other authors, Martin Karplus, Martin Field, Jalen Gao, Walter Thiel, and many, many, many others. And they are based in a kind of effective hybrid Hamiltonian. So the energy in this approach is the quantum mechanical energy for the small system that you compute by means of your favorite quantum mechanical approach, a classical potential, and an interaction potential between the quantum parts and the molecular mechanics part. And it's very simple. So this is a kind of electrostatic interaction between the point charges of the molecular mechanics and the electron density of the quantum part, plus a kind of van der Waals potential, plus all these coupling terms that accounts for the classical force field type functionals. Okay, when you have this, you can actually, when you have this, you can couple your calculation to any molecular dynamics code that you are going to practice quite a lot how MD codes work. So once you are in the framework, you can use, I would say, standard packages, AMBA, many others can do this type of KMMN calculation for you. I will give you a few examples of how this type of methods can be used in your research projects. And I think examples are the best to get these ideas. And this is, for example, this is a work of Hansel, a postdoc in the group, and it is an enzyme, but it's an enzyme working on DNA. This is an enzyme from bacteria, and is the family of nick and join enzymes. So if you think in DNA, you should think in a rope. And if you want to replicate, for example, the DNA or transcribe the DNA, what you need to do is to open this rope. And you can imagine yourselves trying to make a hole in this rope and pulling in this direction. It will generate a tremendous torque, a tremendous effort. And after a while, it will be just impossible. This is what in bio is called superhelicity. So if you try to unwrap duplex, you will generate superhelicity, and this need to be relaxed. Otherwise, everything stops, full period. In eukarya, we do this through enzymes called topoisomerases. In prokarya is this family of enzymes that are called MOP. And MOP-M is a kind of mystery. It has been a kind of mystery for many years. And why? Because if you think about what you have to do to relax tension, is very simple. So you have a lot of tension, then you cut the fiber, then you allow to relax, and you join again. It's very simple. It's what, any kid would think. So you try to open, you generate stress, cut the fiber is relaxed, and you have to join again. So chemically speaking, you need to transfer a phosphate from the DNA to the enzyme, and then from the enzyme to the DNA once it has been relaxed. And the most obvious solution, chemical solution for this, is to have the same reactant and product. So if you transfer the phosphate from a hydroxyl, transfer it to another hydroxyl. And then from this hydroxyl back to the first hydroxyl. This is the most obvious thing, to have very similar reactant and product. And the problem of this enzyme was that there is not any residue with a hydroxyl there. So there is not tyrosines that were characterized. When a friend of us, Michael Gold, solved the structure, it appears that the mystery will be solved, because they will find something in the binding site that will look like a tyrosine, perhaps a serine, or something, a water something, but there is nothing. There is nothing in the binding site. You can see the binding site here. There is nothing that justifies how the enzyme is able to capture this phosphate. And what Hansel did was to think in an alternative mechanism that turned to be true, but was quite heretic at this time. That was that the phosphate was transferred from a hydroxyl to a nitrogen. This is very, very strange. It's very, very uncommon because the donor and acceptor are different groups. But anyway, it was the only possibility it looks to us as reasonable, and then we explored this. And of course, when you want to explore a chemical reaction, you need to play with quantum mechanical partitions. In this case, this is the partition, so this is the system that is tackled at the quantum level, and this is the entire system that is considered at the classical level. Okay, this is the type of calculations we did. This is a calculation that is called potential energy surface. What you do is that you move slowly this phosphate from this position to this other position, and then you compute how the energy changes. This is the details of the calculation. It's not needed here. But at the end of the day, what you have is a kind of free energy profile that will give you an idea of how the energy evolves along this reaction. And how can you know that this is correct? In this particular case, it was straightforward. So we make a lot of predictions. We predict that this histidine was crucial. What is the histidine? That this histidine was crucial. If they mutate the histidine, the enzyme is dead. Then we predict what was the barrier around 14 kcal/mol. Then we asked experimentalists, they did the experiment. It was 14 kcal/mol. But, okay, you can say it's just luck. So what we decided was to look at the active site and predict many changes in the catalysis that will be true if the model is true, and will be very difficult to justify otherwise. For example, I don't know, we predict what was the effect of substituting this arginine here by a neutral residue, and you see that actually you have an increase in the barrier, which is not obvious looking at the structure, but the calculation predicted, and it turns to be also true. There is an increase in the barrier. So at the end of the day, what you get from this type of experiments is a kind of mechanism, explanation of how an enzyme works. I'll give you another example, and this is the work of Vito, a postdoc in the group, and this is a nice collaboration with Philip Hollinger in Cambridge. And here the thing was much more aggressive. It was not to determine the mechanism of an enzyme that exists, but to create an enzyme from scratch. And it was a Philip idea to create or to modify an already existing enzyme to create a new function. In this particular case, he wants to make a polymerase that was making a strand, not of DNA, but of this strange molecule here. It looks like DNA, but instead of a phosphate, you have a phosphonate. So it's a neutral. It's a neutral moiety. And this changes completely the properties of DNA. So in terms of recognition, it's the same. In terms of structure, it's the same. But it's not attacked by nucleases at all. So if you think in biomedical or biotechnological application, phosphonates are a great idea. The problem is that they're difficult to synthesize, so it was like a nice idea to try to develop a polymerase that catalyzes phosphonate. If you think for a while, it is very difficult. We start with this enzyme that is a viral enzyme, and this enzyme is prepared to catalyze the incorporation of DNA, so things with a phosphate here. So has evolved through millions of years to stabilize the entrance of this phosphate. And now that is negatively charged, now you have a neutral group. And making the enzyme means to make something able to recognize this neutral and then being able to catalyze the transfer of this neutral group that is completely different to what nature has done. It was a lot of work, mostly by Philip, to make mutations. I mean, rational drug design help a lot, and this is not a tremendous problem to make this bind the protein. So there were something like 10 site-directed mutagenesis changes in the enzyme. But what about the reaction? And the reaction is very, very tricky, because to get the reaction, you need to follow how the molecule behave through time. First thing that you need is the binding site, how the binding site looks like. And this, of course, we didn't know it because we didn't have the structure. We modeled the structure, and then Vito make some effort to actually see how the binding site, the reactive site, should look like. And for the polymerase expert, it was a surprise, because here you have the residue that is going to be transferred. This should be in normal conditions a phosphate. You see here that this is not an oxygen, so this is a phosphonate, but the rest is very similar to a normal polymerase. So you have the two magnesiums, and you have an arrangement that actually reminds you quite a lot the normal polymerase one. Despite this is not charged. So you have the two magnesium, you have this coordination of aspartic acids. Okay, so you have a reasonable setting for the reaction. Okay, let's So let's look how it happens. So this is, remember, this is the entry nucleotide, and this is the already existent. And so at the end of the day, all this has it's not very excited about transfer. I will show you in a second another one where it will transfer. This is the same, but now I'm in a monitor here, and this is the residue that should transfer. And then what we did was all this that you see here is quantum, all the rest is atomistic detail, but it's classical. And then what we forced, and you are going to learn about bias in sampling, what we forced was the approach of these two guys. And this is like a very basic reaction coordinate. I'm sorry I didn't put the last plot. This was like a preliminary plot. This is a transition state. And after that, after a while, you will have this transfer, and then you will have the PPI. So this is a reaction that we predict. And what is for me, was a big surprise, is that actually when you look, and I insist this is not the final plot, but the value is about, the final value of the barrier, it is about 9 gigamoles. And this is really exciting, because this is the barrier of a normal human polymerase or viral polymerase. So this enzyme that we create from nowhere is actually able to catalyze the reaction with the same speed than the normal polymerase. And is able to do this with a substrate that has nothing to do with respect to a normal DNA. That is in fact neutral. I don't know why this is not working well. Well, starting from here, we analyze many details. We are now working in a new enzyme with improved properties, able to catalyze other incorporations. But I just want to show you the power. And this is my last example of the KMMM. And this is a work of Juan and Monse in the lab. And here things were even more aggressive. And this is the advantage of simulation versus standard bioinformatics. So in simulation, you can actually do things that have not been done before, because are not a statistical based method. So in here we play with the idea to create enzymes based on DNA. You know, most enzymes are protein. There are a few ones that are RNA. These are the so-called ribozymes. But there is not any natural enzyme made on DNA. But it would be great, because DNA is more resistant than RNA. You can work better in the lab with DNA than with RNA. So why not create enzymes based on DNA? And the idea was to make an enzyme that was able to, in this particular case, link two segments of nucleic acids. And of course, for us, to do something, we need a structure. But we were very lucky that in 2016, a group of crystallographers, Hobacker and all, and others, got the structure of the first DNAzyme. It was a big assignment because it has a structure that has this kind of hairpin type of structure, and it looks like it would be possible to simulate the reaction. So I asked Juan, that is a theoretician, he's an experimentalist, okay, let's try to simulate how the enzyme works. And then after 1 month, he came to my office and said, the enzyme doesn't work. So it was impossible to make catalytically active the enzyme that appears in the PDB. And the reason was very clear. In order to have competent enzymes, when you have a phosphate transfer, you need to have magnesiums, and there were not magnesiums in the active site. There were magnesiums here, but these are structural magnesiums. We need to put magnesiums there, and we did it in a very simple way. This is a Poisson-Boltzmann type of calculation. It shows that there are 2 places where it's very likely to have magnesiums, and from the following, I will put 2 magnesiums here. Of course, then you need to prove that your binding site is stable. This is our state, sorry, the previous state, the post-catalytic state. It is stable. The pre-catalytic state is stable. You see nice configuration, with 2 magnesiums. This is the place where you are going to have the transfer of the phosphate from this guy, to actually have the join the 2 strands. Everything looks very reasonable. Remember, these 2 magnesiums are going to coordinate this phosphate. Can we make with this model predictions before launching the simulation? I don't know.
It's okay for you, but I don't know.
I will move from. So this is the model. So the first thing that before running the simulations that are very costly, we take a look at whether we can predict something with the model. And something that we tried to predict was whether the enzyme has a specificity for joining RNA or DNA. Experimentally, we knew already that it joins RNAs, so that you need the 2' OH. But when you build a model, it's completely unclear why you need RNA. Why it should not be DNA? Because this is the 3', and the 2' OH is, there. It's doing nothing. So why there is this requirement for RNA instead of DNA? And what we did was very simple. We make these changes from DNA, from RNA to DNA, and what you find that immediately you lose the reactive configuration. Okay, you see in this particular case, it is actually moving. When you change you remove the 2' OH, the Packer-in change conformation, and then all the reactive funnel is lost, you lose the linearity, and actually the catalysis is impossible. So it was a nice and non-obvious nice prediction. But go back to the reaction. This is what looks like. Here is a plot similar to the previous one, but this has 2 dimensions. This is the transfer of the phosphoryl group, and this is the transfer of the proton. You can see here, it's doing nothing. On here, the reaction starts. This phosphate starts to migrate. Very interesting, these magnesiums move apart a little bit. They are now stabilizing all this very unlikely charged situation. And this phosphate is now actually joining, and when it joins this hydroxine, the proton that was here has jumped to this position here. So there is like the approach of the phosphate, there is a single, is a 1-step asynchronous, so there is a single transition state, but actually the transfer of the proton happens downhill at the very end. Okay, Let's go and compute the free energy associated to it. This is the activation free energy. It's 24 kcal, so it's a high barrier, but it's exactly the experiment. And these are really great news because it was a very risky type of calculation. So it's great. We get quite good results, so we were very happy. But this is a bad value because the reaction should be exothermic. So how it is exothermic? This is one of the things that you start playing with quantum and with classical. In order to be exothermic, you need to recover the enzyme. So remember, at the end of the day, the proton was here. This is a very likely situation. So this proton will migrate to this other phosphate. So it will jump through a water molecule to this position here, to this position here. This is a barrierless process. And once it's here, it will migrate through other water molecule to this PPI. And this is a very common trick of nature to catalyze things is to leave PPI alone. Remember from your basic biochemistry courses, you know that ATP, MMP plus PPI, a lot of energy. And this is because PPI love to be protonated. So this is actually an exothermic process. And furthermore, because when you have PPI, it likes to go to the solvent. And this is a classical simulation. This is, in fact, this metadynamics. What we did was to actually remove the PPI. When it removes the PPI, actually it drives the two magnesiums spontaneously, so you don't need to do anything. They just move away. And believe or not, at the end of all this process, we'll recover the crystal structure. So the crystal structure was useless in terms of predicting catalysis, but this is what you get at the end of the catalytic process simulated. Of course, at the end of the day, we have an endothermic process, and we have values that fit the experiment, but furthermore, we understand what the experiment was telling us. There was a post-catalytic state. So we analyzed the role of magnesiums. Remember, in our simulations, we put two magnesiums. There were no magnesiums in the crystal, so we invented the magnesiums. So we test what was the importance, and then we substitute magnesiums, one or the other, and you can see that the reactive surface disappears. So it's not catalysis if you don't have magnesiums. So at this point, we were very happy. We submitted the paper to this glamorous journal, and the editor say, okay, that's good, but this is a statement from Bihai Pandey. In science, like in life, it's bad to fall in love with model. And this is actually something that is completely true. You need to validate your models. And from now to the end, I'm going to insist a lot in experiments. So you need experiments to validate what you are predicting. And in this particular case, the key point was to check that these two magnesiums were present. We did this very simple order, catalytic order. That means to look at the dependence between the rate and the number of magnesiums. When you plot the log-log relationship, log gives you the number of magnesiums involved in the catalysis. It got 2, but it means nothing because it could be other 2. So to prove that there were these 2, what we had to do was to substitute the oxygen by a sulfur. Why? Because when you have a sulfur, sulfur doesn't like at all the magnesiums. So if you substitute a phosphate by a thiophosphate, you should expect a dramatic decrease in the reaction. And actually, it should be chiral specific. So we substitute, and it was more than 1 year of work in the lab to substitute the S, the R, and you can see, the reactions go down dramatically. And this agrees with these oxygen coordinated magnesiums. But the last proof was to actually substitute magnesium by manganese. If you do that, manganese loves to interact with sulfur. So if you take a phosphate, substitute by a thiophosphate, and you have a decrease in catalysis, but then substitute the magnesium by manganese, and you have a recovery in catalysis, the only possibility is that these magnesiums were real. I'm not going to go into the details, but looking at these plots, this is the enhancement. When you add increasing quantities of magnesium, it's absolutely clear that our model was correct. And the last thing that you can claim is, okay, perhaps what happening with the proton, and there are some experiments that are called kinetic isotope effects. In short, you substitute protons by deuterium. The deuterium are heavier, and then catalysis is lower. If the proton is involved, and this is indeed what we found. We have a kinetic isotope effect that fully agrees with our model. So you can do a lot of things using quantum mechanics when you play with DNA. But I'm going to stop here and move to the following level, is when you have a system of 100,000, 10,000, 100,000, up to 1 million atoms. That is a normal area of work at the classical level. So it means the field of molecular dynamics. And you will have many, many talks on molecular dynamics. But the basic idea is very simple. You use Newton, equations of motion, and you use a very simple definition of the Hamiltonian, of the potential energy, that is this formalism that was raised by many people in the 70s. Actually was incorporated in the first code in 1976 by Otto Warshall, who called the program. The first MD simulation, and this is what was worth the Nobel Prize for Martin Karplus, was of a protein, was done in Europe, in SICAM, by the way, in 1976, and was published in 1977 in Nature, and was an ultra simple simulation. So it was a very simple protein in vacuum. It was simulated for a few picoseconds with a very poor force field. It was impossible. Any journal will publish the simulation now. And this is a type of evolution of the field. Up to here is real. Here are predictions. But it gives you an idea of how MD has evolved. So the first simulations were picoseconds. There are now simulations published in the order of milliseconds. And multi-millisecond simulations are possible, and you can probably combine several of them to reach close to the second for a small system. The original model contains a few hundred atoms. There are no simulations done with millions. 10 millions have been published. I know has not been published yet, but I know that Karisa Summamatsu has done using, I think it was Oak Ridge supercomputer, has simulated 1 billion atoms. So it's 1,000 million atom system. So just incredible, considering just 40 years ago it was 200. You are now doing massive simulations with many replicas for a given system. You are storing the data, and you can predict that. I think it's already possible to do a drug target binding type of study in the real time scale that this happens, and it will be possible, this is more speculation, to simulate, entire pathways or signal transduction pathways at this level. The weak point of molecular dynamics are sampling. So you need to be sure that the process you want to follow is in the time scale of your simulation or of your combined simulations, or otherwise you need to use enhanced sampling. So enhanced sampling methods that will enrich the sampling through a specific pathway. And you are going to learn a lot about this. And the second weak point is the force field. Because the force field is very simple, and it has to capture very complex interactions. So in the case of nucleic acid, in the case of DNA, for many years, the force field was a completely disaster. So when people was running simulations on proteins in the 80s, it was impossible to run a simulation for DNA. The DNA fell apart. So my group has been working quite a lot in developing force field. We developed BImBS, that was the first force field able to reproduce experiment in a multi-nanosecond time scale. It has some caveats, and a few years ago we developed BImBS that is probably one of the best, or the best force field for DNA. It's mostly the work of Ivan, but many, many people in the group was involved. it implies more than 6 years of work. So when you use a force field and you claim and you blame that it's not working, think that the poor guy that developed this stay for years in an unglamorous thing trying to reproduce experiments, and it's not easy. Also, the force field was open 1 year before publication, so people could use it and detect if it was some problem. And at the time it was published, it was very, very heavily tested. In fact, all the trajectories are in a database that you can download. You don't need to trust us. You can check by yourself. I'm not going to go into many details, but just show that MD has now predictive power. So you can predict many things in many different aspects of DNA. And I encourage you, if you have a problem, to use the force field and use new generation molecular dynamics. I'll give you a couple of examples of very recent work in the lab to show you what's the power that you have with current MD simulations of DNA. And the first is a work, this is the experimental, here was Monse, the theoretician was Vito. And it was like a side product project, so we were not interested in that. So this project jumped on us. I mean, we were interested in triplex, and triplex are made when there is one strand of the DNA that is, of the duplex, that is polypurine, the other is polypyrimidine, and then you add an extra strand of polypyrimidine. And in general, this is not any problem, but we were interested in what happens when one strand of the DNA, one strand is DNA and the other strand is RNA. And when we found them, we found very strange behavior, actually give us to focus our interest in these hybrid duplexes. So this is a normal DNA, the two strands are DNA, a normal RNA, the two strands are RNA, and these are the hybrid strands. So in this particular case, this will be a DNA-RNA, and this will be the opposite, an RNA-DNA. So in this case, the difference is what is the purine strand and what is the pyrimidine strand. So I will call in the following, these are the controls, right? In green will be always dpu r pi, means that the DNA is purine, polypurine, and the RNA is polypyrimidine. And rpu d pi, the RNA is purine and the DNA is pyrimidine. So just the opposite. And so Vito did some simulations in here. This is a little bit for DNA expert, but at the end of the day, okay, what you have is the following. So let's look at this, for example. This is the definition of the grooves, but all are the same. So these are how the grooves look like in a DNA duplex. This is how the grooves looks like in an RNA duplex. The books say that a hybrid is like an RNA, and this is not. So it's in between the DNA and an RNA. But the interesting point here is that was a kind of asymmetry. So the green, that is dpu r pi, so the purine in the DNA strand, is closer to a DNA. And the yellow, that is the purine in the RNA strand, and the pyrimidines in the DNA strand is closer to an RNA. And more or less the same information is in all the other plots. When you are working DNA and you find this type of behavior, immediately came into your mind that there's going to be a difference in stability, because typically RNA is more stable than DNA. So you will guess that this will be less stable than this other. But of course you need to test it, and this is what Vito did. Vito take a look at the energy, and the first that they realize is actually in terms of stacking, it's very good to have the pyrimidines in the DNA strand. Why? Because then you have the stacking of thymidines, which is better than the stacking of uridines. And this explains a part of the difference in stability that we predict. And the rest comes from the backbone. So I'm not going to go into details. You can see here the big difference. But the backbone is much happier when you are in a rpu d pi than in a dpu r pi. These are predictions. Let's go and do the experiment to check that these predictions are correct. This is a boring table, but just take a look to this square here. You have here is the control with DNA, the control with RNA, and this is a hairpin. This is okay, look at this. This is a different percentage of guanine and cytosines, okay? And this is a R-pu-D-pi, melting temperature 61 degrees, and this is R-pi-D-pu, melting temperature 35. Dramatic difference. Under physiological conditions, this won't be stable, this will be stable. But then you can say, okay, is it because the change or thymidine and uridine? You can take and substitute, these are synthetic experiments, the thymidine by uridine, deoxyuridine, and you see that indeed there is a reduction in the stability. Or in the reverse, you can substitute here the uridine by ribothymidine, and there is an increase in the melting. But they never reach this value, which is exactly what we predict. So if you move from hairpin to normal duplex DNA, it is exactly the same, and this is, I'm extremely happy because this is a non-obvious prediction. But why? I mean, at the end of the day, what you learn about biology from this. So if you take a look at the results, you can make two very, I think, very strong predictions. And the first one is that actually R-pu-D-pi are more alike than R-pu-D. I'm sorry, this is, I put exactly the same. So what we can predict here is that, you know, the green D-pu-R-pi is more DNA-like than the R-pu-D-pi that is more RNA-like. This is the most stable, this is the less stable. This is far away from RNA. And we knew from a previous paper that actually to make this hybrid to be catalyzed, to be clipped by the RNA polymerase, it has to be very different to RNA. So we can make a prediction here that R-pu-D-pi will be worse substrate than D-pu-R-pi. And this is what Monse proved here. So you can look at here at the results. So this is the control. Okay, the control is DNA. This is another control, RNA. This is not degraded. You add here increasing quantities of RNAs, and you can see here that up to 10 minutes, you still have the hybrid. In 12 minutes, it is degraded, but here you still have substrate. In here, that is what we predict. This is the DPU. That is a better substrate. In 5 minutes, it's almost done. In 10 minutes, it's completely degraded. So it's a prediction that tends to be right. But then we make another prediction. So R-pu-D-pi are more stable than R-pi-D-pu. Sorry, this is again a typo error. So these are more stable. So we predict that then it would be better in terms of CRISPR strategy. So when you are running CRISPR, you take the DNA and you add an RNA strand that has Cas9, that is, you know, a nuclease, but can be anything, and then the RNA direct to the specific genomic locus and is actually cutting the DNA. And then you can process DNA in other different ways. So in principle, you can tackle one strand or you can tackle the other strand of DNA. You can tackle, you know, the Watson strand or the Crick strand. And what we show here, our calculation suggests, is that it's much better if you tackle the pyrimidine strand, because then you will make, of DNA, because then you will make a much more stronger duplex, and the CRISPR efficiency should be larger. I'm not going to go into details because these experiments are very difficult. They were done at CRG by Roderick Guigaud and other friends, but this is what you find here. This is the efficiency that you get on CRISPR, and you can see that actually it was done with different sequences, but you can see that always the improvement by tackling the pyrimidine strand is very, very significant. I think this is 10 to the -5 and 10 to the -4 in terms of significance. Again, this is a non-obvious prediction that could be made thanks to molecular dynamics simulation. And this is my last example. It is a crystal. I don't know if there are crystallographers in the audience, but to get the crystal is a kind of magic recipe. You never know why you get a crystal. So you mix things, and then suddenly you get a crystal. Once you get a crystal, this is a typical setup. This is the word of Antonia. So you have a buffer with the molecule you want to crystallize, and then this is the buffer. This is a hanging drop. It is evaporated, and at the end of the day, you're lucky you get a crystal. When you get a crystal, it is projected, you get a diffraction pattern, and then you solve the structure. Why you get a crystal? What some molecule crystallize and why it crystallizes in a given system and not in others. So we were interested in this, again, by kind of, it was not planned at all, but we were interested in crowding, to be honest, but we center our attention to this sequence of DNA. It's called the Druidicus of the decamer. It's a very popular sequence of DNA. It has been crystallized many times. So there are many, many structures in PDB of this specific sequence, and actually, they fall in 3 different crystal lattice symmetries. So this is the most common one, but there are 2 others where the structure has been crystallized. So the idea was done very simple. So let's try to build a crystal and run simulations and see what happens with this crystal lattice, whether the DNA was the same, it changes, what's happening. So then Antonia set up all these simulation setups. So takes all the different symmetry, take a control simulation in solution. These are the cells. For the MD expert, this is a pain on the neck because you don't simulate a single DNA. You have to make all the copies, and then you need to reproduce the crystal symmetry. So these are very complex type of simulation. So you need to set up the cell very carefully to be sure you are not introducing artifacts from the simulation. And for example, just to give you an idea of the effort, in here we are talking about systems with 1 million atoms. We are taking 28 different systems, more than 40 microseconds of duplex dynamics. If you go to the duplex level, this is millisecond scale information on the duplex. And this was, of course, possible just because of praise support, because it's a very intensive type of simulation. Okay, what we got at the end of the day. This is one of the crystal symmetries, and what you find here is a heat map of the sampling that we get of the duplex. So this is a very, very dense map because we have millisecond data, close to millisecond data, and these are regions that are explored, and this is plotting or projecting a given base pair step, so 1 in, cytosine, cytosine, 1 in, and we project it into 2 helical parameters. This is the roll, for example, and the till. And this will be, the twist, that is, and the roll. Okay? What you see here is the region which is sample, and the dot here is the experimental structure. So you feed the experimental data in terms of the crystal structure of the duplex. It's impossible to distinguish really the crystal DNA and the DNA that is simulated in the crystal. Which is good. It means that the forcing makes sense. But then we look at another different things. It's the center of mass of all the helices. We have many, and then we explore. And we explore in different planes. So this is the XY. It means how, this gives you information about how the helices move in these directions. And they don't move. It doesn't matter which crystal lattice you have. You don't have, this kind of diffusion. But then look at what happened when you look at the z-axis. There is slippery. The helices slip in this way. And you can claim in this and this. And you can claim that maybe a force field error, but it doesn't look like, because in this case, they stay stable. So the take-home message is that these 2 crystal lattices are not stable. They shouldn't exist. They shouldn't be there, but they are. While this is a very straightforward way to get a crystal for duplex DNA. Of course, there are experimental evidence that these crystal lattices are right, and simulations say that are wrong. So we do, to explain what is happening, Antonia did something completely. This is amazing. It has its own life. So Antonia did something really unique, that was to take a look to the papers, not to the PDB. And if you take a look to the papers, you realize that in all cases there is a bivalent ion. It changes, but all the cases is +2. There is an alcohol that what it does is to make more stable the DNA. You have a diol that is actually helping to organize, to aggregate the DNA, but in all the cases it's the same. And the only difference is in this guy, spermine. In these two crystals, they put a spermine, and in this other crystal, they don't. So it looks like it may be the difference in here, because our simulations were in normal conditions. We didn't add a spermine. And the spermine is a +4 charge. And all the crystallographers would say that the spermine does nothing, because it's not clear in the crystal. So you don't see the density of a spermine. But it was obvious what to do. I mean, this is our simulation that it's behaving very well. This is displacement in the XZ, in the X-axis, Y-axis, and Z-axis. And you see that it's actually behaving very well. And these are the simulations that were not working well, where you have these distortions in the Z-axis, big oscillation in the Z-axis. And for this simulation, it was done with magnesiums, with water ions, blah, blah, blah. Then we start increasing quantities of spermine, and you see how actually then the crystal lattice became stable. And we repeat for the other crystal lattice and actually became stable. So take-home message is that we are able now to understand, to reproduce a crystal structure, and not only that, we are able to understand why these additives that are not visible in the crystal are important. And what is the spermine doing? You see here what it's doing. This is a snapshot, really. And you see spermine, we put different quantities of spermine based on what the crystallographers suggest to us. And this is a spermine all around. So spermine is a kind of glue that is keeping the DNA close to each other. And I think what we are having here is an image of how the DNA should be in a crowding conditions in the nuclei. Why is this spermine that is there and is making such a wonderful context is not visible in the X-ray? You just need to plot this density of spermine into a cylindrical coordinate space, and then what you would see is that there are not regions where spermine has a special density. So there are not regions where spermine likes to be more than other regions. So spermine is not here. It will be moving like a snake through around the DNA. And there is not a specific region where it stays. And this is not why it is not visible in the X-ray diffraction pattern. So those things that you don't see may be important. And this is my last slide before a short break that we're going to do right now, saying that repeating. So by doing MD simulations, atomistic fossil, you can really tackle quite complex DNA systems, but there is still a challenge. Remember, we want to simulate the genome at the base pair resolution. So we need to move now. We can tackle systems that are 50, 60. We can tackle one nucleosome, for example. Even two nucleosomes can be reproduced, but we are far away from this very, very long fiber that we want to simulate. So if it's okay for you, we'll make a break, 10 minutes break. And when you come back, if you have questions on this part, I will be very happy to answer. And then we'll move to the mesoscopic part of my talk. Okay? the practical part is going to focus mostly in this part. Okay, the QMMM and the MM part already you will have many lectures and many practices. So he will focus in this mesoscopic part. So the challenge here is how to use all that we learned from the small system to deal with large systems. And our starting point was was an harmonic model. So the idea here is that DNA, or physiological DNA, is, for many things, an ideal duplex. And you can represent this as pairs, planes, that relates to 3 translation and 3 rotational degrees of freedom. Then you can assume that actually the deviation from ideal geometry is penalized by an harmonic term, that it is like a stiffness matrix and a reference geometry. That is the ideal twist or the ideal roll of the DNA. How we got this stiffness matrix and how we got the equilibrium values through molecular dynamics simulation. So the idea is that you run MD simulation, then you focus at all the different base pairs, and you compute the covariance matrix in the helical space, and in one of Einstein equations say that by inverting the covariance matrix, you get the stiffness matrix. This is basic ideas from Wilma Olson and later Philip Blancas. And what we did, actually, this is mostly work of Pablo, Jürgen, and many others. Within the ABC consortium, we took a bunch of duplexes of DNA that contains all the base pair steps. Base pair step means, for example, AT, and this is paired to AT, right? Or GC that is paired to GC, or, this is a base pair step. 2 bases interacting, 2 bases interacting. And then when we did that, we found that actually tetramer effects were important. You can see this. So this is, for example, I don't know, let's take this one. This is twist. If white means that this base pair in this tetramer context has a twist value that is above normal. If you see that it's red, it means that it's below normal. Blue is above normal. So the classical ideal models of DNA, everything should be white. This is wrong. The nearest neighborhood model will say that something is either red or blue, but not at the same time. So, for example, it is what the nearest neighborhood model will predict. And you can see that this is also wrong, because, for example, here you have blue and red. So this base pair step, depending on the tetramer sequence, can be over twist or under twist. So tetramers are important. And the worst thing are these triangles, because this means that there is not a single minima. There are at least 2 minima. That is not, the distribution is not normal. So it's not elastic model. And this is what is shown here. So this is a projection in 2 dimensions. See on a slide of a given base pair. We have all of them. And this is a Gaussian, perfect Gaussian. This is a Gaussian, but correlated. This is not a problem because we have the cross terms. But this is not something that can be catched by a harmonic model, neither this one. So our approach, and this is the work of Jürgen, was actually to take the trajectories, to do some kind of machine learning clustering to decide the number of minima you have, and then applied in this specific minima, in this specific cluster, apply the elastic model, and at the end got for all the base per step and different elastic models, so different stiffness constant, and then combine all of them using, and this is basic statistical mechanics, and actually is inspired in empirical valence bond theory, but you can get these equations from, second, third year physics textbook. At the end of the day, what you have is a Hamiltonian that you can implement into a metropolis Monte Carlo. Jürgen will explain you the details, but something we did was move out of the helical coordinates, because at the end of the day, when you do this type of thing, you have a metropolis, an ensemble of base pair geometries, but biologists want to see structures. So we recover the backbone through an empirical relationship between the backbone geometry and the helical geometry. For example, depending on the twist slide, you know that the DNA should have a B1 or B2 conformation. These are two conformations of the backbone, right? So in other words, the geometry here is actually dictating quite a lot of the backbone geometry here. So it means that you can implement, in addition to this metropolis Monte Carlo, a probabilistic term to decide what was the backbone conformation, then a little bit of refinement, and at the end of the day, you have an atomic resolution picture. So this is a plot of how it looks in terms of average properties of the DNA, so the end-to-end distance, the torsion, and what you can see here is that it converges very quickly. This is what you are unable to see, the different contours. These are the same calculations with different length of the Monte Carlo trie. The average values reproduce very well, but here you can go into detail, right? What you have here, I don't know what is the red and what is the black, but one is the experiment and the other are Jürgen's formalism. You cannot distinguish. And this is MD simulation in, I don't know, perhaps in red for an oligo 55 bases long, and in black or in, well, the other color means Jürgen's metropolis simulation. You cannot distinguish. So and these are things that are not helical. These are things that are Cartesian. This is, for example, the grooves. So the quality of the ensembles that you get is very difficult to distinguish from the real atomistic one. It is the same shown here, but what is important is the speed up. So this is the same simulations for oligos of different size. So larger the size, higher the cost. And this is for different computers, 8 CPUs, 16 CPUs, 64 CPUs. So in this particular case, let's say the longest oligo we have simulated through atomistic, it will take about 2 years to finish in this computer. Of course, you run it in a supercomputer, but in this small cluster, it will take, remember you have a lot of water, it will take 2 years. And the same calculation in Jürgen's code will take, 15 minutes. So the speed up is in the order of 10 to the 5. So, and this is important because this allows us to study very, very big systems. So remember, we want to move to the chromatin levels. With this method, you can study systems with 1,000 base pairs without, or several thousand base pairs without a problem. We can modify this model by adding to this very simple helical representation of DNA, adding proteins. We can add proteins, we can add, for example, nucleosomes. In Jürgen's model, nucleosome is very simple. It's a single bit that has some excluded volume to avoid nucleosomes hitting each other. It goes through a van der Waals. So with this, you can actually introduce epigenetic modifications if you want, making some nucleosomes more likely to interact with others. And it has a de-vehicle type of approach that helps to avoid, collapsing, the DNAs from all the sites into the nucleosome. Of course, you need to parameterize the histones. The DNA is not a problem, it's well parameterized. You need to parameterize the histones, and the approach was to use sedimentation curves and images to actually parameterize the parameters, to parameterize the interactions of the histones with the DNA and with other histones. This is the basis of our model. But remember, now we are losing completely any physical, losing most of the physical concept. Remember, we use quantum mechanics to parameterize force field, we use forces and dynamics to parameterize the mesoscopic model. But at this point, everything has loose connection with the real physics of the system. So we need experimental restraints to maintain a sense in the calculations. And I'm going to explain very quickly the type of experimental restraints. You're going to play in the afternoon with this. But the type of experimental restraints that we have and the way in which Diana, Jürgen, and others in the group have implemented. This type of restraints are of 3 kinds. Images, sequences, and 3D sequences. So how we know where the nucleosomes are? In principle, we could test the position of the nucleosomes, but this is a very, very complex problem. Because you have many nucleosomes, many positions, the nucleosomes are stiff, so we have experimental data. And this is called MNase digestion. So the idea, and you will have one program we have developed that is called nucleosome dynamics, that is in the BRE you're going to play with this afternoon. The idea is very simple. So you take your cell, you break the cell, and then you treat the chromatin with an enzyme that is MNase that cuts the DNA when it's free, but cannot cut the DNA if it's protected by the nucleosome. So after digestion with MNase, you have you'll have eat all the nucleosomes here, while this nucleosome here will be there. Well, this DNA here will be there. So then you digest the proteins, you digest the RNA that can be around, and then you have this sequence of DNA that you sequence by ultra sequencing, Solexa type thing. So at the end of the day, what you have are reads. So if you have a read there, it means that it is a DNA protected by a nucleosome. So then you can use this type of plot. This is the experimental throughput. You can transform this into, this is called nucleosome column picking. And we know Oscar, Othgen, and Diana, and many others develop methods to actually transform this very noisy signal into this nice signal from which we place the nucleosomes. One example of how this is useful is in here. This is a result from Diana, and this is yeast. When you modify glucose, instead of feeding with glucose, you feed with galactose. And so yeast is not prepared to digest galactose, right? It's not ready. And to digest galactose, galactose has to be promoted into glucose and then going back to the standard glucolysis cycle. So the enzyme that do this type of catalysis is not active under normal conditions. So if it is not active, it means that it will be blocked. This is the transcription factor binding site. This is the beginning of the gene. And the transcription factor binding site is blocked by a nucleosome. So the transcription factor wants to do the job, but actually it cannot because it's a nucleosome there. And see what's happening when you activate these conditions. So the galactose instead of glucose, this nucleosome disappears, and this is what the red signal means, and then this is activated. The same happens even worse if you add alcohol. So changes in nucleosomes are really crucial to understand how the cell reacts to changes in the environment or changes in the development. But it has many difficulties to understand how the nucleosomes are based on the data. So this is the raw data. And okay, you can say that, well, perhaps it is a nucleosome here. Yes, maybe another here, but it's completely unclear what is here. And it's not clear at all. If you have 1, 2, 3, and so you need to and this is because the signal that you detect is not the signal of a single cell. These are not single cell experiments. They are done on 1 million cells. So what you see as an experimental truth is actually an average of many cells where things are a little bit different in each of one. So you have one cell that the nucleosome is here, another cell that the nucleosome is here. The average will be like a mountain where you can predict that the nucleosome is there. But actually it's not there at all. It's in 2 different alternative positions. So Jürgen has developed a method he will comment to you on how this signal can be deconvoluted into families, unique families of nucleosome strings that actually are built one on top of the other to actually make M families. So it means that instead of a single nucleosome string, we get like thousands of possible nucleosome strings that, when combined, reproduce the experimental data. Of course, we need to add more data. So this is a small piece of nucleosome. These are 4 nucleosomes, and this is how we know that this is true, is because it fits a lower resolution data. For example, something that Jürgen and others have developed is a way when they generate the families to see how these families should be combined when transformed into structures. So you have this family here, then you build a structure, and you see the ability of this structure to feed this experimental data that is called micro-C. How this high-resolution, low-resolution experimental data came from, I will comment on high-C, but high-C, micro-C, all this is very similar. So the idea, and how can we implement this into calculations? And this is the work of Diana in the lab. So the idea is that your DNA in the cell is not in a random way. In the nucleus is not in a random way. It's not extended. There are regions that are in contact. So if these two regions are in contact, and then you cross-link the DNA, these two regions will be bound by a covalent bond and will remain bound. If you degrade now the enzyme, the DNA with an enzyme with a restriction enzyme, the restriction enzymes make cuts in cohesive ends. So you cut here and you cut here, for example, and then these streams are cohesive. If you put the ligation conditions, they will join together. If you reverse the cross-linking now, you will have these things. Of course, you will have many normal DNA, but you have these things. And these are chimera. So in terms of sequencing matching for the bioinformaticians in the audience, what you will find is that you have a segment of DNA, you don't know where to map in the genome. So part of the DNA will map in this region of the DNA of your reference genome, and the other part will find miles away. This is indicated that these two parts in the original chromatin were close. How we transform this experimental data into experimental data gives this type of plots that are contact plots, and these are called topological associated domains. Right? How we transform? Well, we use a little bit of math. I'm not going to use a fractal theory to actually transform this contact into distance. And for the simulation people, we use Brownian dynamics to actually develop a set of configurations of the chromatin that reproduce the data. So we never try to get one structure because this is wrong. The signal is given by an ensemble of structures. And this is what we get for the simulation expert is a kind of time average restraints what we develop. We use other restraints. Remember, we need restraints because we are losing the physics. For example, I don't know, we have data on the telomere-telomere distance. This is experimental data. We have information on the nuclei. So we know the shape and the volume of the nuclei. This is a very simple experiment. And we can add other information. And these are unpublished results. This is a technique that is called oligopainting. This is immunofluorescent type. So what you do is you label you tag a proof of DNA with a fluorophore, and this proof of DNA recognizes a specific sequence in the gene and give a signal. You can see here, this is a technique is called STORM. It's a Nobel Prize winning technique. And you can see here that with this technique, you can label two specific genes. So you label two specific sequence of two specific genes. And you can measure this and actually compute what is the distance between these two genes. And you can put all together this type of information. And at the end of the day, what you're going to have is a kind of dynamic picture of the chromatin. So what you have here in the left is what we believe is a G1 version of G's chromatin. And what you are going to see at the right, this is another kind of simulation I'm not going to explain to you. This is not Brownian. This is discrete. But this is the transition of the chromosome 3 dynamics, of the chromosome 3 of mouse, the dynamics of transition between two different cells of the cell. So these are simulations, but are simulations based on the implementation of experimental restraints. And I think I'm going to stop here. It was an example of how can you get information, but give me just 1 minute to comment this. This is, for example, the level of accuracy that you have, the level of resolution. So this is what happens when you take yeast and you put under conditions of stress. oxidative stress. So what we want to do, this is experiments that we take cells and add hydrogen peroxide. The objective was to generate mutations and see what happens when you generate lesions in the DNA, and then the cell reacts to correct these lesions. And eventually, in this process, will generate mutations. So what we are simulating here is a kind of model of cancer. What happens in the very early stage of cancer when the DNA is damaged and the cell is running like a chicken without head, trying to correct these lesions. And this is in one specific region what it happens. So these are changes in the fiber, but this is the type of resolution we have. This is Jürgen's model on the situation in the control where this gene is very happy, is not active, is not happy, is not damaged. And then you damage the DNA, this gene needs to be repaired. In fact, this particular gene needs to be active, and you see how dramatic is the change in conformation between this situation and this other situation. There are many more changes in the global chromatin that actually in all the cases means a decrease in the compactness of the chromatin. And this is going to be my last slide. Just explain you that the work I have summarizes the work of many people here. And I think we have time for a few questions or comments if you want.
Okay, thank you, Modesto. Thank you very much for the clear lecture, the perspective also that you give for the future studies on this field. So I will expect some questions from students particularly interested in DNA studies. So please.
Hi, I was actually curious about Diana's model, the Brownian part that you were not talking about. Could you maybe give some extra info on that? Because I think that the video is very interesting.
Yeah, so the way in which, so the way in which it works is that you assume that the DNA, in principle, will work chromosome by chromosome, and then we put together, right? But think in a single chromosome. What you assume is that you have a bit, and the separation between bits is equal to the resolution of your experiment. In the case of micro-C, we have 145 base per resolution. In the case of high C 2.0, we have in the order of a few hundred, 300-400. In the case of normal high C, you have 1,000. So it depends on the type of data we have. And then these are bits, and the distance between bits is a kind of a spring. And then the bits are Lennard-Jones particles, and the parameters are adjusted as to warranty the proper density of DNA in the nuclei. So I mean, we know what is then we start adding constraints on top of that. These constraints, I mean, are flat well potentials, like if we're NMR. When a contact is never seen, we put a repulsive potential because otherwise we overcompress. And then we use multiple replicas, and we use standard time average. At the end of the day of the simulation, this is Brownian Langevin dynamics. At the end of the simulation, you have an ensemble. And then what we did was to select, we cherry pick structures from this ensemble as to warranty that a maximum of results are found, a maximum of experimental restraints are preserved. So typically, in the results I show you, we reproduce in the order of 95 to 99% of the restraints with a reduced number of families. We force that none of the structure explains a lot of the variance because this will be not realistic. So we know from microscopy that there is not any contact that stays more than a given percentage of time. So at the end, what we have is a diverse ensemble that reproduce the shape. So then we use this shape to fit the nucleosome fibers. So the shapes are a kind of cloud where we fit the nucleosomes. And this helps a lot. Because if you look at the nucleosome itself, it's very easy that you get a configuration that makes completely sense, and probably it's true if it was not the overall structure. So this is then, the shape allow us to do a cherry picking of the families which are locally possible, and this is how we rebuild. And we have done this for yeast, but we have also data for humans, for fibroblasts, in fact. This is how the method works in a nutshell.
Other question? Curiosity, guys? Anybody? I have one, actually, but I prefer to leave the stage to the students, but they seem to be shy. So you are involved such many years about the force field development on DNA. I would like to have a perspective in this field. So my question can be also extended to protein force field. So it's one of the limitations of our simulations, the accuracy of the force field. Basically because we consider the same type of residue, glycine or in your case, thymine, guanine, whatever, as the same, whatever it is in the DNA. So my question is, how far we are to have a kind of system-dependent force field for each specific simulations, or if this is the direction where to go, also using machine learning and this kind of methods, or what do you think about that?
Well, this is a good point, of course, yeah. I don't know. So DNA is quite simple, compared, for example, to RNA or proteins. It's the ends are different to the rest, but this is a small part. And you can think, of course, in making sequence-dependent parameters, introducing polarization. I'm not completely sure, so I never see that at the end of the day this gives an improvement really in the results at the end of the day. About machine learning, of course, this is clear that is a future. My only worry is that you need data, and there is not so much data there to actually fit. So you can think in the massive amount of quantum data, but to reproduce for example, the stacking, you need to climb to couple cluster with triple excitation, so really get quantitative value. And of course you're interested in getting in solutions. So yeah, I'm not. So it's clear that machine learning will solve all the potential problems, but how the hell you get the data you need for a machine learning and don't have an overtrained method? Yeah, so it's a
challenge. Maybe quantum computing also may happen if we, in the future, we are able to use them. So if there are other questions from the audience or question, guys, no? So thank you again, the speaker. Nice time for coffee break, but we extend a little bit with some delay in the schedule, so 10 minutes. So be back at 11:10, right? 11:10, yeah, 10 past 11, okay.